construct a rule interpreter using nothing but analogical matching, but the rules are going to look a little different. Not too different, but a little different because of that one-to-one constraint. Is that what we're doing in our heads? I don't know. Open question.
All right, well, thank you very much. I welcome our next speaker, Dave Kieras. Please go ahead and take the screen. Whenever you're ready.
Here we go. Are we there?
Yep, you're good.
Okay. There's the title. Let's get going. I don't know if John did this on purpose, but following after Ken Forbes, we've gone all the way from extremely high level cognition. Well, in this one, we're going to get really down and dirty even with experimental data. Okay. A little bit of background. This is using EPIC, cognitive architecture, that was focused on modeling human performance, which is the area in psychology that is mostly concerned with how well people can do things, usually under the assumption that they've already learned how to do it. Okay, what we're going to focus on in this talk is modeling methodology, as illustrated with some models for visual search tasks. What's a visual search task? It's pretty important both theoretically and practically. The idea is you show people a screen full of objects, and they have to find the specified target object in that display or just simply say whether it's present or absent. We vary the number of objects on the display and what distinguishes targets versus distractors. We measure the time required and the accuracy. Okay. Mandatory diagram of the architecture, but the key thing to point out here is that this has both perceptual processors and motor processors. These are explicitly represented. Each of these expands out to a pretty complicated beastie. In contrast, the cognitive processor has nothing in it but a production rule interpreter and a production rule working memory. Okay, more about all that later. Okay, here's what Alan Newell said in 1973 in his famous paper. But I think this is actually the precursor to the whole idea of cognitive architectures. He recommended that we build complete processing models that not only have these various mechanisms, but especially the control process that connects them together. He recommended production rules as a way to represent that control process. He also pointed out that the most fundamental fact about behavior is that it's programmable, it's changeable. So you have to know the method your subject is using to perform the task. That means subjects are acquiring a strategy, what Newell called a method, for doing the task, and you got to have that explicitly represented in the model. But interesting fact, this is still true at Newell's time. This is what he is addressing in large part. It's still true that mainstream cognitive theory models have little role for perception and motor. The control process is rarely explicit. Okay, looking at this from a cognitive modeler point of view, there's a problem of how do you construct an explanatory model with a cognitive architecture. You're going to have some combination of mechanisms that explain the phenomenon. The control process is one of those. Our traditional approach all these years has been, well, we fiddle with the model until it fits the data, and then we present the final results and declare victory. But the traditional approach doesn't tell us various important information, like which mechanisms are actually needed and what they contribute. And if there's more than one combination that will work, which one is best. We're also discarding useful information along the way, like why do some models not fit? Many years ago, Susan Chipman asked me this question, and it's had a lot of influence ever since. So the solution is an explanatory sequence. Instead of presenting the final model, we'll start with a starter model and add or modify mechanisms in a predefined order and step by step, and then we'll see how each mechanism contributes to matching the data. This is actually a systematic way of doing the logical process of abduction, which is inference to the best explanation. That is, given a set of possible premises and an observation, find the best combination of premises that entail the observation. So our cognitive architecture basically gives us a set of possible premises in this sense. So what's the meaning of the best explanation? The proposal here is that it depends on this predefined order of adding or modifying mechanisms. What's a good order? I'd argue it's the epistemological basis. What evidence is available for the existence and properties of each architectural mechanism? So the perceptual and motor mechanisms are actually the most observable, huge empirical literatures going back to the 19th century. Thus, these are relatively known. The cognitive mechanisms, though, are more hypothetical. We only view them indirectly through perception and motor mechanisms. Not very observable, but we can say, following Newell, that it has to be able to execute a task strategy at the bare minimum. So we include these mechanisms and modifications in this priority order, put the known perceptual and motor mechanisms in first, then we'll modify the assumed task strategy. Third priority is to modify those perceptual and motor mechanisms in well-supported ways. The fourth priority is to add to the cognitive mechanisms beyond simple strategy execution. Villain in this piece is this idea of covert selection attention, which has been extremely popular in cognitive theory, but in this scheme, it has less priority to be put in. Okay, I'll illustrate with some models for visual search. This tasks and data. Here's 3 different tasks, okay? First one is, can you find the 2 shape? Is it present and surrounded by all these 5 shape distractors? The color task, is there a red object amongst all these green objects? Conjunction task is, can you find the red vertical amongst all the green vertical and red horizontal distractors? Okay, so in each of these cases, you're pressing one button for present, another button for absent. Okay, and the number of objects on the display, the set size goes from 3 up to 18. These examples are 18 objects. Okay, we'll record the reaction time and the error rate. Okay, let's get into the mechanisms that we're going to start with. There's known perceptual mechanisms of visual availability or acuity. The probability that you could see, for example, the shape of an object depends on its eccentricity from the fovea, the size of the object, and the property in question, like the color, orientation, or shape. This has been around for well over a century. Here's a sort of psychophysical way to represent it with a availability parameter theta, and that gives us a set of curves that look like this. These are example values for color, orientation, and shape to go with those tasks. Okay. Another known perceptual mechanism is crowding, lateral interference, or flaking effects. There are other names for it. If the objects are too close to each other relative to eccentricity, the integration of the properties into objects is disrupted. We'll try this demo. Look here, compare what you see with what you look here or here. Okay. Relevant to these tasks, because the display area is held constant, so the more objects you put on the display, the more closely spaced they are on the average. So the simple model for how crowding works here will just scramble the properties among the objects that crowd each other with a probability parameter phi. This happens after each eye movement or when the display appears. Key idea that scrambling these properties can produce illusory target objects, illusory distractor objects, and illusory blank, or that is unknown property objects, depending on the properties that are actually available. Okay, known motor mechanisms, I don't have to say much about that. We know a heck of a lot about the timing and accuracy of eye movements and simple manual movements. It's also a common hypothesis that's been adopted of action slips. You have the correct intention, but you just simply make the wrong action. Here we'll represent that as you want to press the present button, but with some slip probability, you just hit the absent button. Okay. Okay, the hypothetical cognitive mechanisms is EPIC's cognitive processor. It's a very simple production system. The only thing it does is to execute a task strategy supplied by the model in the form of production rules, assuming that learning the strategy has already taken place. And we'll see how well this strategy concept fits by the goodness of fit of the model. So EPIC has a very simple production rule engine. I won't say more about it at this point. Okay. Here's the starter initial strategy called the basic search strategy. It performs any present absent visual search task, and it's a fastest reasonable strategy. It's fast, it's because it doesn't require that you fixate each object before responding, which saves time. It can do that because it uses information in peripheral vision. And the strategy itself won't be responsible for any errors. The only errors come from messed up perceptual information or one of those action slips. Here's the production rules in pseudocode. Nominate a possible target object, top objects, plural. Choose an action. If there's a nominee that has all the target properties, then respond present, you're done. If there are no nominees, respond absent, you're done. So one thing that happens here then is that, for example, in the shape task, if you can't see the shape of something, then that's a possible target and you may want to go look at it. Okay, but if you can see all the shapes there and they're all distractor shapes, the fives in that case, then nobody gets nominated as a possible target, so you can respond absent when the trial is done. So you only have to move the eyes as much as it's necessary to resolve the state of particular objects. Because of peripheral vision, you can see more than one of these at a time. Okay, so let's start an example explanatory sequence. So here's that with the shape task. It's a prototypical search task. It's non-trivial, takes some time. Here's the reaction times. This is 2,500 milliseconds up here. Here's the error rate. That's like 0.14 up here in terms of 14% errors. Okay. What I'm showing you here, the red lines are for the target present trials. Okay, it takes longer as you get more objects on the screen. This is the error rate for target present trials. You say it's absent, but it's actually present. These are misses in our conventional terminology. Notice how they increase the set size. This is for the target absent trials. Notice that they're, so here you're saying there's a target there and it isn't. That's a false alarm. And in this case, they're basically constant with set size. In fact, this is true across all the conditions, okay? Okay, and here's our negative RT. It generally takes longer and more steeply sloped. Okay, so let's look at what we get when we try to put mechanisms into a model. As a minimum, we'll start with a basic search strategy and just our availability mechanism. And if we increase the availability from left to right across these plots, see that the reaction times go from very flat and fast. They start increasing, they increase more, and then they're very much longer than the data says. We're getting a pretty good fit here. The green arrow means we're on, okay? The red arrow means, oops, look at that. We are predicting 0 errors. Okay, let's add the action slips. Okay, that doesn't affect our RTs, but now we're getting these are on top of each other, but we are now getting false alarms at this constant rate, which we estimated at just the false alarm rate for the slip error rate. But we're not getting any misses at all. Well, let's try adding the crowding effect. Okay, what's going on here? Well, the RTs change some as we increase crowding from left to right. See, well, look at that. The miss rate is starting to go up and way up. Okay, look at that. We get a pretty good fit here. Well, what's going on? Well, the crowding increases with the set size. The more crowding causes more illusory distractors. And the strategy says, remember, the strategy says absent if all the objects look like distractors, so it becomes more likely that that happens, and thus we get more misses with increasing set size. So we know exactly what's going on. This is looking pretty good. Now to sort of flesh out this explanatory sequence notion, let's see where we violate that priority ordering. Say instead of crowding, let's try a strategy modification. If the target's not found after a certain number of fixations, we'll stop and respond absent. So a limit of 8, if we apply that strategy modification, a limit of 8 fixation gives us a good match to the miss error rate at set size 18, but oops, not so good at set size 12. We could start messing with that and going down a rabbit hole about how to try to make that fit. Well, look at that. There's no need to go down that path because according to the priority order, a known perceptual mechanism should take priority over the less observable strategy change. Okay, so here's our final refined fit. We nail this pretty good with a basic search strategy and these 3 parameters. It's straightforward account. The RT depends on the number of eye movements, which depends on the set size and availability. Crowding increases with set size, causing more illusory distractors, causing the strategy to produce more miss errors. Well, that's pretty darn simple. Okay. Now I'm just going to have to summarize the next two conditions very briefly. Just a reminder of the color task. That's what it looks like. RTs are very flat and fast. The error rates are pretty flat too, but they're getting a little more misses than false alarms. I collapsed all the steps together here. Interesting. There's no combination of basic search, slip errors, availability, and crowding that will give us both of those key characteristics of the data. Try changing the strategy. To get the flat and fast RTs, we just say don't move the eye at all. And then it turns out varying availability will give us the miss rate that we want. That was easy. How about for the conjunction task? Now this is a more complicated, more subtle task, and an awful lot of blood has been spilled in the cognitive psychology literature just over what happens in this task. In terms of this system, though, what's happening here is that we have two highly available properties, color and orientation, and the crowding mechanism will scramble these properties between the objects, and the result is we'll get a lot of illusory targets and a lot of illusory distractors resulting from that. So that's what the data looks like. There's a summary there. If we vary basic search, availability, and then crowding, well, we can match the RT slopes. Crowding causes these illusory targets, and there's so many of them, we'll get a massive false alarm rate, just literally off the chart, and no misses happening. Well, we can modify the strategy to make a double check eye movement to the apparent target. That'll eliminate crowding, and that prevents the false alarms, but now the absent RTs are way too long. Still not enough misses. Impose a 3 fixation limit with another bell and whistle to confirm the absent situation. And now we get a pretty good alignment with the data. The punchline here is that this conjunction task doesn't require anything exotic. It just means the strategy for accomplishing this task is more complicated because the stimuli basically are more affected by the perceptual issues. Okay, so what have we learned here? The explanatory sequence for all these tasks use the same visual mechanisms of availability and crowding, same motor mechanism for eye, hand movements, and slip errors, and a different strategy for shape, color, and conjunction. So the major difference between the tasks is just the strategy. So Newell was really right about the control process. That, in fact, is kind of where all the action is. So remind you of the priority order here and what we've learned here. We put in these known perceptual motor mechanisms. We did some strategy changes or modifications. We didn't have to add or modify the perceptual motor mechanisms, and we didn't have to add any cognitive mechanisms. We only have the original strategy execution system. So this popular notion of covert attention is simply not needed. Okay. Here we go. All the fits are there. I'll just point out that if you throw all 48 data points, you get these extremely nice goodness of fit metrics. Okay. So what we now know about visual search is we can explain this in terms of these known factors and simple strategies. These contrast with the prevailing theories, which you'll find in the cognitive psychology literature, which almost completely ignore the visual factors, give little or no role to eye movements, believe it or not, lack explicit programmable control processes and strategies, and rely on this informally stated hypothetical mechanism of covert selective attention. And two of these major theories that you may have seen are these two. These models show that the visual motor factors and strategies suffice. We don't need a mechanism that is more hypothetical and less empirically grounded. There's a little bonus. The same family of models also explains the individual subject data very nicely. Okay. So I'll conclude. Newell was right about complete models and explicit strategies. The explanatory sequence provides a way to systematically construct these cognitive architecture models. And this priority order is a key part of that. And in fact, we've been following this approach since the beginning when we've been constructing epic models. But now we better understand its philosophy, its logic, and methodology. Okay, I'm done.
All right, thank you. A question, how do you know, like what measures do you have for uh, whether or not an incremental improvement to your model, like the addition of a strategy, was warranted?
Oh, like going from one step to the other? Well,
Yeah.
I didn't put the goodness of fit metrics in here just to save time. But of course, yeah, R-square metric, absolute average relative error, average absolute error for both RT and ER. Um, yeah, so at each step in the way, I mean, you can use those metrics to see whether you've actually improved things or not. But it happens that the so-called eyeball fits are pretty persuasive here. So I didn't clutter the slides with those metrics. Does that answer your question?
Uh, Maybe. So I'll
Okay.
get to that follow-up in a minute. First, I'm going to skip around. Greg Trafton asks, could you explain a bit about how your models fit individual participants?
Yeah, if I had another half hour, okay. But see if I can say this in one sentence or two. It turns out the subjects in these three tasks, they cluster into various groups that are basically showing the same pattern of reaction time and error rate effects. And you can try to fit each of those clusters of subjects with one of these models. And it turns out that you can do it with just basically small variations on the models that I've shown you. For example, in the shape task that produces data that looks like this, it turns out there's one cluster of subjects whose data is extremely curvilinear, really flattens out in their reaction times, and they have huge error rates. Well, this is just say, well, they're pulling the plug like at something like eight fixations. They're stopping and responding absent. That nails the data really well, okay? But everything else they're doing is the same as the other groups, okay? Slight parameter differences. Some people, there's one group that does this task with extremely sloped RTs and almost no errors at all. That means they're working much more in the mode of fixating every object, and you can capture that by very tight availability parameter. They pretty much have to be looking at the object to tell what shape it is. Okay. So,
All right.
and that applies to the other two task conditions as well. That same kind of approach.
From Andrew, implementing simple strategies requires a control mechanism. Is it possible that attention is that control mechanism?
Well, it depends on what you mean by attention. And if you really digest the psychological literature on attention, starting with William James, you can learn a lot. If you wanted to put EPIC on the scale of attention discussion and then use that terminology, EPIC implements what you could call a very late selection mechanism for attention. That is, it's not until the production rules decide what to do with the sense data that, you know, they're looking at a particular object and say, yeah, that looks like the target. Let's respond, yes, okay. Is that what you mean by attention? I don't think it's sort of the popular meaning of attention, but it would fit into that framework, but it's a very different idea from what most people usually mean by attention.
So forgive me when I likely mispronounce. A follow-up from Mariecki. A more complex model would fit the data better, so is the improvement good enough? I guess they're asking for a follow-up on your metrics.
Let's see. I respond to that. Okay. What's interesting in this sequence, which unfortunately I had to abbreviate here, is that some of these fits, the fits you get in these first two steps, are amazingly bad. Okay, they're really awful. Okay, as you make these strategy modifications here, they get less awful, but still pretty gross until finally it gets pretty good. So, yeah. Quite a bit of the time you can rely on eyeball fit to tell you where to go, but of course the actual quantitative metrics are the better that fits. And I like to use all three metrics here because each metric behaves differently. Like, see, the R square for these flat, fast RTs is 0. It has to be. That's how R square works, okay? But look, the average absolute error is only 4%, and the is only 18 milliseconds, and the relative error is only 4 milliseconds. So you're getting different information here. Error rates are, if you get very small error rates, well, a 1 percentage point difference was 100% error rate. So these are forced to be relatively high, but in absolute terms, the difference in proportion is only 0.004, okay? So I like to use all three metrics, and because they do tell you slightly different things, okay? But our fits are all pretty good, so I'm not sure what the issue is.
All right,
Maybe
thank
I have
you.
to follow up.
Frank Ritter, is there a paper on this yet?
Yes, there's almost nearing completion is a technical report with a fair amount of literature review and all the stuff spelled out blow by blow for both the group and the individual subject level of analysis. And send me an email and I'll make sure you get a PDF of the report as soon as it's done, which is going to be in a week or two, I hope. Okay.
All right, only one more question so far in the chat from Shantanu. For crowding, feature conjunction, and illusory effects, do you consider the impact of growing receptive fields in a hierarchical model of visual processing, and how postulated feedback mechanisms wherein deeper layers help route lower layer eye movements, how that may impact reaction time and error rates?
Okay, we're basically talking, I believe, about the neuroscience of how crowding effects would work. And quite a bit of the crowding literature is concerned with that, but hasn't really converged in anything I've read so far on a good mechanism for how crowding works. But it is believed that it has a lot to do with the receptive field geometry, or they often call it the integrative field geometry, which gets these receptive fields get bigger with greater eccentricity. They sort of have a funny fan shape kind of going outwards from the fovea. And it's believed that, and this has a lot to do with the mapping of retinal positions onto visual cortical positions. There's a notion of cortical magnification, which is an old idea that has a lot to do with this. So yeah, there's a lot of interesting things that can be done here at the neural level. It hasn't converged to a very good characterization of exactly what's happening when crowding goes on, which is why I had to put in the simplest model I could think of crowding effects, which is just this property scrambling thing, which a lot of the authors in that area kind of allude to. So I don't know if that's directly answering your question, but that's the most I kind of know about it at the neural level.
All right.